I'm going to go through, I got a few questions on email that were sent to me, or that for folks that aren't here, so I just want to address those. They were good questions. One was asking about, I sort of mentioned it in passing last time. Let's see if there's a question that's here, where you have a charge that's moving in a potential field. And there are a couple different questions that come into play for that. So let me.
Like with the graph.
With the graph, right.
It's like all the way like in, I want to say maybe like 2000.
Okay, but they come up here too. We'll go back to that one, but they come up here with these equipotential maps as well. I know that's not really what you're asking, but it's relevant here. So let's take a look at that. Like number 18, this is on the last spring 24, number 18, where I place an electron right here at point B, place an electron right there, and I ask what direction will it move. So at point B, it looks like it's at a potential equal to 0 volts. And I always like to draw this picture where I know that electrons will move from high to low potential, or excuse me, protons. Electrons will move from low to high potential, right? That protons move from high energy to low energy, high potential to low potential. So in this case, an electron is going to move, well, towards point C, right? Because it's moving from low potential to high potential. Now, if I were to graph this, my graph would look like this, Vx. V starts out at 0, and it moves up to 30. So an electron, this is point B, this is point C, an electron would move in that direction, in the direction of increasing potential. Now let's look back at that 2018 question. So that one is just saying that electrons are going to move in this direction. If it was a proton, by the way, what direction would it move? It would move towards the low potential, from high to low, from 0 to minus 30. Okay. Let's look at 2018. Oh, you say 2018? Okay. That doesn't mean you won't see it, just because those are in old exams.
I think it was like the only one here.
Okay.
It was like right from the concept test.
From the concept test?
Yeah, remember we did a couple in the concept test?
Well, I'll just make them. So say, for example, I have a graph of potential versus position, and it looks something like this. And say I have, I don't know, a point here, a point here, a point there. We'll say this is A, B, C. A proton at point A, a positive charge at point A, is going to move in which direction? To the right. It's going to move in that direction, in the direction of decreasing potential. Actually, what it would do is that it would oscillate back and forth in this well. An electron, on the other hand, would move to the left, an electron, or it would oscillate back and forth. If oscillation is the option, that's the one that you put, if it's in the right direction. Okay? Does that clear that up a little bit?
So, and if a proton was at B, it would go right to the next one, or it would go left?
Yeah, so if a proton was here, a proton is going to move from high potential to low potential. So it's not going to move to the right, because that would mean that the potential would be increasing. It's actually going to move to the left. So a proton right here will move in this direction, or it will oscillate in that potential well. Alrighty? All right. We can come back to that. There might be some other questions about that, but let me address these other questions that students sent in. This student's in quite a few questions. He said, how do you figure out the angle counterclockwise from the x-axis? Like, response question number 1, part B. So here, if y'all want, we can work through this. We've already worked through these, but in D, I want you to measure the angle counterclockwise from the x-axis. Looks like, I don't remember where that, I don't recall where that final vector was. Let's just say that that vector was right there. And I say that this angle you find to be 30 degrees. That's not what it is for this. I don't know what it was. 53 degrees below the negative x, like that? Okay, so 53. Then, okay.
Yeah, it was 20 below the negative x.
Okay, 20 degrees below. And then the way that I would report it, because I want it measured from counterclockwise from the plus x-axis, and I'm going to want that too, okay? So make the text doesn't, I cut and paste it. And so since it asks that, that's what I want. I want it measured from the plus x-axis. So if you don't do that, you're only going to get half credit, okay? So the way to do it, I'm going to draw my coordinate system right there. I'm measuring this angle. So this is 180 plus that extra 20. So the answer would be 200 degrees from the plus x-axis. Okay? I want that. I want you to make sure you get that right. And then how do you know if the angle is above or below the axis? So question number 5 on spring 23. Well, if it's above or below, we can come back and work some of these vector problems. But it sort of depends where your resultant, your x and y components add up. So for example, if I have 2 vectors, one pointing up and one to the left, that's going to have a resultant vector that is in this direction. And then when you find this angle, that's going to be above the negative x-axis. Or if I have 2 resultant vectors that are in this direction, those are the x and y components, then that, when I add up those 2 vectors, that angle is going to be below the x-axis, the positive x-axis. So the way that you determine if it's above or below is really just drawing your x and y components. Remember, I always like to draw pictures all along the way. Like I usually have 2 or 3 pictures of the vectors along the way, and it helps me to see is it above or below the x-axis. I recommend that you do the same. I know not all of you feel like you need to do that, but I feel like I need to do that. And y'all aren't that much smarter than me. So, like, I would draw the pictures if that was the case. Alrighty? Some of you are quite a bit smarter than me. I get that. But, yeah, we can do the whole problem. Let's go to one that we haven't done. Okay, so let's just do spring. This is spring 23. Yes, this is the exact same problem. All right, let's cut and paste the text, change the figure, change the charges, and then let's go through. So step A, sketch the electric field vectors. Those electric field vectors are going to go here. I'll call this Q1, and I'll call this Q2. I'm going to have one electric field in that direction, that's E1, and another in that direction, that's E2. I can find this angle. Oh gosh, I left the number off. Did anybody get the number off the video for this? It's 12. It's a 12, 9, 15. So it's like a 3, 4, 5 times 3, right? So that's 12 meters. That means that, by the way, this distance is 15 meters. And that angle, the angle that's right here, that's 53 degrees. Right? 53 degrees. Y'all okay on that trig? I use the Pythagorean theorem. I use the inverse tan to find that angle. All right. If you're struggling with that, stay after. I'll help you with it. I'll walk you through it. All right, so next, that's part A. I finished that. Part B, show your work for calculating the x and y components. So for part B, I first have to calculate E1 and E2. E1 is 9 times 10 to the 9th. Times Q, which is 9 times 10 to the minus 9, divided by 9. So that gives me, cancel, 9 newtons per coulomb. And then E2 is 9 times 10 to the ninth. 75 times 10 to the minus 9 divided by 15. That cancels 15 into 75. So that 5 times 9 is 45 newtons per coulomb. So those are my two electric field vectors, the magnitudes. But E2, further, I have to determine the x and y components of E2. E2x is 45 cosine of 53. And E2y is 45 sine of 53. Hey. Scale what? Look at you. Yeah, you're right. Sorry about that. So that's squared. That means that this is equal to 1 Newton per coulomb. And then, gosh, what is this? 3? Oh, even better. All right. Sorry about that. So that's going to be, that'll change this to be 3 in both of these cases. 3 cosine of 53. So that would have been, if I had forgotten to square and you had all this other stuff right, that would have been just half off. And then, of course, that would have made C and D wrong, but if you did C and D correctly, and you got the right answer, I wouldn't have counted off for those at all. So 3 cosine of 53, that's 1.8. And then 3 sine of 53, it's 2.4. Okay? So newtons per coulomb. All right, so at this point, I like to draw this again and just make sure I know my vectors correctly. So I have E2x is 1.8 in that direction, and E2y is 2.4 in that direction. And then E1 is 1 in that direction. That really helps me to determine the magnitude of the final electric field. So part B, that's the end of part B. This little picture is optional, but will really help you to determine where your final vector is. Actually, no, there's one more step. So I have to now also find the x and y components of the final vector, in which case it's going to be 0.8 in this direction and 2.4 in that direction. Those are the x and y components of the final electric field vector. That could be part B or part C. It still needs to be done. Then for part C, I find the magnitude of the electric field. That final vector is going to be in this direction, and the magnitude is going to be the square root of 0.8 squared plus 2.4 squared. You might know what that is right off. 2 point what? 2.5 newtons per coulomb. And then to find the direction, the electric field, I find this angle right here. That's the inverse tan of opposite over adjacent, 2.4 over 0.8, and that's 72 degrees. But I'm asking for it from the positive x-axis, so I really want to know that angle. So my final angle is going to be 180 plus 72, which is 252 degrees from the positive x-axis. That's that answer. So that's the magnitude, and that's the angle. And then for the final part, is just finding the potential. This is a little bit easier. I find the potential at that point. I'm going to sum up the potentials due to the individual charges, V1 plus V2. That's going to be 9 times 10 to the ninth, 9 times 10 to the minus 9, divided by 9, and that is a positive charge, plus 9 times 10 to the ninth, negative 75 times 10 to the ninth, minus 9, at the 9, divided by 15. And so that gives me 1 minus, that was what I did earlier, wasn't it? 44 volts, is that what the answer is? 1 minus 49. 9 minus 45, yeah, so negative 36. Okay, that's that first one. That's 5 questions, y'all. That's like almost 20 points on the exam. So make sure you know how to do that. If you did vectors okay last semester, you should be okay on this. It's really just vectors. That's really what this question is. You know, not the electric field is not even an important part of that question. Okay, and number 2, you want to draw the electric field lines. Oh, here is one where they have the same sign. That means that the electric field lines are going to be pointing out. So I also want to have twice as many. Wrong, drew that wrong. I want to draw the arrow going into the negative charge and into this negative charge. Let's say I'm looking for 5 to 6, so I need to have twice as many, so we'll just do 2 more there. I'll be looking for the direction of those vectors, that they're in the right direction, into negative charges, out of positive charges, and also the correct number, the ratio. So since that 2 coulomb is twice the 1 coulomb, it should have twice as many field lines. And then I can draw the potential line. Just going to draw it so that it's perpendicular to those charges, or to the field lines. 4 to 5, something like that. All right? Okay, this last one, remember, first to find the speed of the electron, A, remember voltage or potential, a change in potential is equivalent to a change in energy, potential energy or kinetic energy divided by Q. I'm actually going to think about this in terms of kinetic energy. It's actually gaining kinetic energy. It's losing potential energy, but gaining that same amount of kinetic energy. My potential difference is negative 3 minus 6, or 9 volts, equals 1/2 mv squared. That's the velocity or speed of that object, divided by Q. So I can have V equals, well, let's see how you want to do this. I'll put in the numbers here. 9 equals 1/2. This is an electron, so it's 9.11 times 10 to the minus 31 kilograms times V squared divided by Q. The Q is 1.6 times 10 to the minus 19 coulombs. That's both of those, the mass and the charge of an electron is on your equation sheet. And then I solve that for V, and I get a V of what? What do I get? Anybody know? Nobody knows? Y'all do this one? Okay, whatever V is, that's what I get. All right, just solve that for V. And then after that, I want to know what is the electric field. Remember, the electric field is, or excuse me, the potential, I always think of it like this. The potential is equivalent to delta E over delta X. I always try to remember those units. Remember I said that potential can be measured in, oh, I'm sorry, I got that backwards. Never mind. The electric field is equal to delta V over delta X. Yeah, that's right. The electric field can be measured in newtons per coulomb, or it can be measured in volts per meter, right? That the electric field is dependent upon the change in the electric potential. And so I had a delta V of 9 volts over a distance of 0.3 into 9, 30, I think, 30 newtons per coulomb, or 30 volts per meter. Isn't that right? Yeah. So that's the electric field. That's part B. Hey, are those for your response okay, y'all? Yenta, we'll get your question in just a second. Okay on those? Practice, practice, practice them. Hopefully you've already mastered them. Like, hopefully you're not spending tonight mastering them. Hopefully you're not studying at all tonight. You're going to go and have a nice dinner, go to bed, get up in the morning, and be ready to go. But I know that's not usually not how life goes. Yenta, what's your question? 23, number 20. Actually, can we pause on that for just a second? Make sure I got all this.
I found another question.
Okay, hold on to it, okay? Somebody wanted me to do this number 2. Can we do this? This was an email question. So let me do this, and then Yenta will get yours, and then Symphony, your question. So this one's kind of tricky because there's not a good even ratio between the two charges. But a nice simple way to do it is just to say, hey, 1 coulomb is what? Equivalent to or assigned to a single field line. In which case the 2 coulombs would have how many field lines? 2. And then the 5 coulombs would have how many? It'd have 5. So I'd have 2 field lines coming out of there, and then I'd have to have 5 additional field lines. Oops, did that wrong. 5 additional field lines that are like coming in from far away. 1, 2. Oh, I had 1 too many. Oh, shit. All right. So that one was a little trickier just because the ratio here isn't even, so I can't say, well, I need twice as many lines as I have here. But I can just say, well, there has to be 5 lines over here and 2 lines coming out of this positive charge. Alrighty? All right, Yenta, can you repeat that question? Yeah, so this is similar to the question that we had in the free response. Remember I said that there are several questions that are similar to the free response, and this is one of them. You'll see something like this. I like the equal potential maps. I've been doing those more on more recent exams, you probably noticed. I'm moving from point A to point B. Point A has 12 volts, and I'm moving all the way over here to point B, which is at minus 6 volts. That means my delta V is minus 6 minus 12 are negative 18 volts. That means that that charge, which has a charge of 2 coulombs, moves across a potential difference of 18 volts. And I want to know how much energy does it gain as it moves from that high potential to the low potential. And I can do that by saying, well, V is equal to the change in energy divided by Q. And so the change in energy is equal to Q delta V. So Q is equal to 2, delta V is equal to 18, so it's going to gain 36 joules of kinetic energy, actually, as it moves from that high potential to low potential. Again, don't worry about the sign so much. We're just looking for how much energy it gains. So we're not really worried about kinetic or potential or any of that. But you will see something like that. So let me just step through the procedure. Then first you want to determine what is the potential difference. And the potential difference is always the final minus the initial. Negative 6 minus 12 gives me a potential difference of 18. This is like a topographical map. I know you probably don't read topographical maps because in Louisiana there's like no lines on a topographical map, right, because the land is all flat. But here a topographical map would show like a mountain. This is high elevation, this is like a valley, it's a low elevation, and the lines all represent to, a constant elevation, or in this case, potential. So this location is 12, that location is minus 6, gives me a difference of 18 volts. And then returning to our definition about potential to define the change in energy. And the change in energy is going to be just Q times delta V. 2 coulombs times 18 is 36 joules. Good question. You will see an equal potential map that'll have a couple of questions attached to it. Not important, because I'm just asking how much energy it gains. The negatives in those questions will never be relevant to you. I know I wrote the negative, but you can just forget about it. Okay? However, y'all, this negative, it is important that you get the difference in them correct. All right? Because if you did 12 minus 6, you wouldn't get 18, you would get 6. So that is important. Okay?
The same going from B to A. Answer 36.
If it were, so if it were going from B to A, well, that would have to be what kind of charge? To go from B to A? A negative. It would be if it were a negative 2 coulomb charge, it would move from B to A, from low to high potential, and then it would be the same answer. Yenta, is that okay? Symphony?
On spring 22, number 18, it's kind of maps you have, but it's more in like the graph.
Oh yeah, here we go. Yeah, so a proton is at x equal a. Protons are going to move, what, from low to high or high to low? High to low, yeah. Imagine your mountain. Protons, they do normal things. They're going to go downhill. And so that's what a proton is going to do here. It's going to move in this direction. It's not going to oscillate because there's no well there for it to oscillate in. If it were an electron, by the way, what would it do? It would oscillate over this hump right here. We call it a well. It doesn't really look like a well because it's an electron that's flipped upside down. Yeah, an electron would oscillate back and forth in that potential well. But a proton is just going to move to the left. A is the right answer. Okay? All right, y'all, what else? Karaz? This one? With the map of the, about the map of the potential lines? I think that's spring 24, yeah. Oh man, I changed the charge going from 18 to 19? I would not do that to y'all. That was mean, wasn't it? I changed, you see, like it's an, I'm sorry, I heard you. It's an electron here, and then it's a 3 coulomb charge there. What a jerk. Who wrote this exam? I'm sorry. Spring of, who is that? Spring of 24? I know, I was just talking to myself, I'm sorry. Okay, yeah, so I want to know how much potential energy this configuration holds. We've done this in the concept test. If you recall, we had the triangle with the 3 charges. And remember, potential energy, all these words, man, they're all very similar, and the equations are similar too, so be careful. KQQ over R is our potential energy. And so since these are all the same distance apart from one another, the only thing that really determines their difference in energy is the fact that the charges are different. So when I see these, and you're likely to see something like this, I take the product of the 2 charges. So for example, these 2 charges right here, I would label that as 8, -4, -8. Let me show you. So these 2 charges have an energy of 4 times 2, that's 8. These 2 charges have an energy of +2 times -2, that's -4. And then these 2 charges have an energy, a potential energy of -8. Those numbers aren't really the values of potential energy, but I'm only asking if it has positive or negative energy. Like, is it going to collapse altogether, or is it going to fly apart? And here, because it has an overall negative energy, it's going to collapse together. It's going to fall into one another. So it has an overall negative potential energy, because 8 plus -8 plus -4 is a negative number. Karaz, does that answer your question on that? Again, on the concept test question, there was one that was really similar to this. I think there were a couple of questions that were like that. All right, what else? Yeah, Jason?
Number 16 on spring 24.
This one right here? Yeah. It's going to be difficult. So I want to calculate the potential so that the potential is equal to 0. V1 plus V2 plus V3. Let's just determine, so V1 is going to be K times -25. Let's write out the numbers. So that's 9 times 10 to the 9th times -25 times 10 to the -9 divided by the distance, which is 5. This is potential, so it's not squared, it's just 5. That's the distance from here down to point A. I did the Pythagorean theorem to get that. Plus 9 times 10 to the 9, 24 times 10 to the minus 9 divided by the distance, which is 4. Actually, I think it's probably easier to just go ahead and determine the potential due to these two charges. I'll show you why in just a second. Those cancel out. That cancels with one of those, and it gets me negative 45 plus 6 times 9 is 54. So that's equal to negative or positive 9 volts. That means that this charge right here needs to give a negative 9 volts to cancel out that voltage. So I'm going to get rid of C and D, by the way, because neither of those is negative. So I'd say that V2 has to be equal to negative 9 volts. That's 9 times 10 to the 9th times Q2 divided by the distance, which is 3, and that's equal to negative 9. And then I can solve that for Q. That goes away, and that goes away. Looks like negative 3 nanocoulombs, I think is the answer on that one. That was right, right? Those are difficult. I think I lost. Did I lose my mic? I did. I'm going to turn this one on. Those are difficult, but they're not that different from the ones that it's just that you're solving for a different value. So here I'm solving for this charge instead of solving for the overall voltage. But did you see how I did that? I calculated the voltage due to these two charges that I know, and then I set that equal to this voltage, or the opposite of this voltage, because I know they all have to add up equal to 0. Those types of questions, where does the potential or the field equal 0, or what kind of charge do you need here to make the force or the field or the potential 0, I like those. I don't remember if they're on the exam, but I wouldn't be surprised if that was the case. It's been a while since I've written. It's been a week or two. All right? Did that answer that question? Yeah. What else we got? Yeah, Madison. Yeah. So this is like those questions that we had in the concept test, but it's just a little simpler because there's only one configuration to consider. I want to find a point on this line where the potential is 0. That is where the positive and negative pairs of charges are equidistant from one another. So let me show you one that doesn't work. Like point A doesn't work because that distance is smaller than that distance. And that distance is smaller than that distance. And likewise, the two threes are the same distance, but because those are different distances to those charges, the potential doesn't cancel out. So let's see, what is the answer? It's not A. It looks like B is the right answer, right? Yeah, B. Let me show you. So at point B, these distances are the same. These distances are the same. And these distances are the same. I'm looking to find the position that is equidistant to the positive-negative charge pairs that are equal but opposite. And when that happens, then, for example, the 3 coulomb, you'll have VKQ over R plus VK, or K negative Q over R. And so the potential due to this charge and this charge will be equal to 0. And the same is true for the blue and the green pairs. But those potentials will also add up to equal 0. Equidistant from the positive and negative charge pairs. They'll be pairs. There won't be anything that's not pairs. Okay? Is that clear? Sort of, kind of? All right. There are similar questions, I think. Yeah, like number 19 is similar. It's not the same question, is it? Well, that was like the same question, number 19. This one's different. So what would be, this is spring 21. Where would that be? Where would the potential be 0 on that on that line of charges? You might see it. What do y'all think? None of them. Right. There is not a point where I'm equidistant to any of those charges. See here, for example, I'm to that one and that one. That doesn't work. It doesn't work for the others either. Here, like those two are different distances. Here, those two are different distances. None of those work. So the answer is E. My wife and I were having a discussion about my daughter just took the ACT, and we were like, what answer do you put if you don't know the answers? And I think that I think E, like D or E, because like if you have questions that are not, no, I think so. Listen, because like when you randomize the answers, which is what you do, so there is no preferred option for a set of choices. If you have no idea what the answer is, there is no preferred answer because it's random. It's randomized, so you can't cheat it, except for those last options like D and E, because none of these always comes last, doesn't it? Yeah. So I think E is probably the right answer. I don't think C is the right answer. E. Yeah. Yeah. 9 spring 23. Oh boy, yeah, so you would definitely see one of these. They're on every exam mostly. This is the one? Right? All right, so first just pick a set of charges and draw the force vector. So I'm going to imagine these two charges, and the force vector will be in that direction. And then I always like to draw or write my equation, KQQ over R squared, and then look at this mu charge, like this plus 2Q, and ask how is it different? It's different because it's twice the charge as this charge, and also it's twice the distance away. So now I have a 2 in the numerator and a what in the denominator? A 4. Right, so I have 2 over 4, or I should have half the force. So that means due to this charge, I'm going to have a force that's half the size of the original vector that I drew. So that means, well, if they were equal, the answer would be C. But because they're not equal, the answer is going to be B. That bigger vector swings the resultant vector closer to it. But you have to figure out how these vectors are. It's not obvious just looking at it that this is going to be a smaller vector. Maybe it's obvious. I have twice the charge, and I'm twice as far away. The distance from the charge has a bigger impact on the force because it's a 1 over r squared dependence, not a 1 over r dependence. So the answer would be D here. Be careful drawing your vectors. Yeah. Okay, I do that because these are both positive charges here, and so my force vector it's a repulsive force. Likewise here, these two are positive charges, so the force vector is in that direction. But you're right on some of those problems, they're not in opposite directions. They're actually a plus and a minus charge. So for example, what if this charge was negative? Well, I would have this force right there, and then this force would be in that direction, so the resultant vector would be in that direction if it were negative. Okay? Good question. You'll definitely see one like that. There's one on every exam, so make sure you practice. Symphony?
Can you do number 12 on the same test? I'm just confused on answer choices A and B. Like, I know B's the correct one.
Okay. 1 meter to the right or 1 meter, like you can get down to either A or B?
Yeah.
Okay. Well, then, if you know that these others are wrong, which you're right, in saying that all these are wrong, then you can just return back to that good old rule that I want to get as far away from the big charge as possible. So that would be 1 meter to the, 1 meter to the left. Wait, 1 meter to the, yeah, I can't. I'm sorry. Let's return back to this. So I want to first ask, where can it not be? So like over here, the electric fields are both in that direction. those can never be equal to 0. Likewise over here, never equal to 0 because they're both in the same direction. So that gets rid of A, because that's 1 meter to the right of the plus Q charge. Gets rid of C, D, and so I'm left with B or E. All right, it has to be somewhere in the middle here. 1 meter to the left of this one, or 1 meter to the right of that one. Now, which one am I going to choose? I'm going to choose one over here, right next to the plus Q. So that would be 1 meter to the left of the 4Q charge, of the 1Q charge, B. But if you're not sure about that, we can think about it. I have that position right there. I know the electric field due to those two charges, E is KQ over R squared. Now here I have a charge that's 4 times as big. So that means to get the same electric field, I have to be twice the distance away. So if I divide this up into 3 segments, I can see that it is twice the distance away. Here, here. This distance is there, and that distance is twice as far away. But you don't really have to go through all that. Once you eliminate it down to these two, you should be able to choose between these two. Just by using that general rule of, I want to be as far away from that big charge as I can. All right? Yep. Other questions, y'all? Is that it? Okay. Don't leave. I had a couple of y'all that came in. I'm not sure I caught.